In this class, we will study the computational procedure in dynamic programming problem by solving an example problem. So the problem is this: determine u1, u2, u3 so as to maximize u1 into u2 into u3 subject to u1 plus u2 plus u3 equal to 10 and u1 u2 u3 greater than or equal to 0. So this is our the DBP can be minimization problem. Like in the previous class we have discussed the concept of sub-optimization. In that we have cost minimization of cost function, and it can also be a maximization problem also. So this here the in place of r, the return, we have this u1 u2 u3 r1 r2 r3. Okay, and summation, this in the previously we have a summation. Okay, but in this case it is product, that is multiplication logic. So like what we have said earlier, it can be one of these, that is either multiplication or summation, that is pi or sigma. Okay, then u1 u2 u3 then yes, subject to this is u1 plus u2 plus u3 equal to 10 is our design equation. And or characteristic equation, you can say. Okay, now we will proceed to our solution. The solution is let the decision variables be u1 u2 u3 and the state variables be x1 x2 and x3. Let x1 x2 and x3 be the state variables. Okay, and here we are going to apply the sub optimization technique, so that we are dividing the entire problem into stage 1, stage 2 and stage 3 number of stages. Okay, where stage 1 is x1 is equal to u1 and stage 2 is x2 is equal to u1 plus u2. Before that I have, sorry, I can write it from stage 3 onwards. Let x3, I have this decision variable x3 is equal to, let it be our design equation, that is u1 plus u2 plus u3, that's equal to 10. Okay, so this is our the last stage. So in order to satisfy this design equation, you have to consider that as a stage. So this is our stage 3. And x2, let it be x2 is equal to u1 plus u2 only, u1 plus u2 and that will be equal to x3 minus u3 from the above equation. And let x1 is equal to u1, that's equal to, from the above equation it is x2, okay, x2 minus u2. So this is equation number 1, this is 2, and this is 3. And equation 1 is stage 3 and this is stage 2. This corresponds to stage 1. Okay, now the returns, you have to formulate this, you have to represent this problem, the dynamic programming problem. You have to identify the returns here. So the returns are the product. Why? Because we have this, let f1 of x1 is equal to u1. Okay, and this, since we have to maximize u1 into u2 into u3, so we are considering the return from stage 1, it is u1. Okay, and then in the return from stage 2, that is f2 of x2, that's equal to u2 into u2 multiplied by this stage 1 return, u2 into f1 of x1. Okay, and this return should be, the second stage return should be the maximization of this function u2 into f1 of x1 with respect to u2. Okay, so max u2 means maximize with respect to u2 the function u2 into f1 of x1. So this will be our stage 2 suboptimization. Then for stage 3 we have f3 of x3, that's equal to the term will be u3, that is from this u3 into f2 x2, and you have to maximize this with respect to our stage 3 decision variable, that is u3. Now, so this is our problem formulation. So we will proceed from stage 1 to stage 2 to then to stage 3. So since u1 is equal to x2 minus u2, from equation 3 we have this. Okay, so f1, so I'm substituting this u1, which is equal to f1 of x1 f1 of x1, and so here I'm substituting for this, so that f2 x2 will become f2 x2, that is stage 2 problem becomes f2 x2 is equal to maximization with respect to u2, and u2 into f1 x1. F1 x1 is x2 minus u2, so that is x2 minus u2. So I'm writing f1 x1 in terms of u2, so it will be maximize with respect to u2, x2 u2 minus u2 square. Now I have differentiating with respect to u2, because you are applying the Newton's method in order to find the u2 value for which this x2 u2 minus u2 square is maximized. So on differentiating the slope, that means at optimum point slope will be 0. So if you differentiate with respect to u2 partially, then x2 minus 2u2 equal to 0 you will get. That implies u2 is equal to x2 by 2. Okay, then this therefore therefore f2 of x2, therefore f2 of x2, which will be, so u2 equal to x2 by 2, that we found that solution. So the maximum value of f2 x2 will be equal to, so you substitute u2 equal to x2 by 2 in this f2 of x2 function. So x2 into u2 is x2 by 2 minus u2 square is x2 square by 4, so that will be equal to x2 square by 4. So f2 x2, we have the maximum value of f2 x2 we got in the stage 2. So stage 2 is over. Now in the stage 3 we have the problem f3 of x3, another function, arbitrary function, and that is equal to maximize the function u3 into f2 x2, that is the previous solution as f2 x2, that is this is what your optimum solution for the optimum output in stage 2. So that is fed as the input to the stage 3, so into u3. So maximize, and this will be done with respect to u3. So it will become like this: f max equal to maximize with respect to u3. The function is u3 into f2 x2. You have to substitute the optimum value. In the previous case we got it as x2 square by 4. So you have to substitute x2 square by 4 here. Okay, now you have to make this x2 to write in terms of u3, and from equation equation 2 we have x2 is x3 minus u3. Let me yes, from this stage 2 we have, for x2 we have x3 minus u3. So you substitute that from stage 2, that's equal to maximize with respect to u3, and u3 into x3 minus u3 whole square by 4. Now you solve this f3, this function f3 of x3 you have to solve. So maximize this, maximize with respect to u3, and again you apply the Newton's method here. So at maximum value of this function the slope will be 0. So on differentiating you will get u3 into yes 2 into product group 2 into x3 minus u3 into minus 1 plus x3 minus u3 whole square into 1. So and this 1 by 4 I have taken this outside, so that will be equal to 0. So this is not equal, so this is the condition for maximum value. So condition is to be satisfied, that means you have minus 2 x3 minus on solving this x3 minus u3 to take outside, then x3 minus u3 into minus 2 u3 plus x3 minus u3 equal to 0 you will get. The condition will become x3 minus u3 minus u3 into x3 minus 3u3. Okay, you club minus 2 and minus u3, then is equal to 0. So then that means, that implies x3, either x3 equal to u3 or x3 minus 3u3 equal to 0, and x3 is equal to 3u3, or you have to find the value of u3. So u3 will be equal to x3 by 3. Here if we evaluate, that is x3 equal to u3, x3 equal to u3, that means the condition as explained, x3 equal to u3, that means x3 is from equation 1 we have. If you go back to your equation 1, then you have the stage 3 equation, that is x3 equal to u1 plus u2 plus u3 equal to 10. So that means u3 is equal to 10. From this x3 equal to u3 you will get x3 from stage 3 equation 1 x3 is u1 plus u2 plus u3, that's equal to x3. Okay, that's equal to u3. So that means at the stage 3 of optimization, you will get u1 plus u2 plus u3 equal to u3 itself. Okay, so in the stage 3 we are optimizing, or you are maximizing the u3. Okay, so and this is what do you mean by x3 equal to u3? Then the next case is x3 minus 3u3 equal to 0. So x3 is 3u3, u3 is equal to x3 by 3, and x3, and this is equal to 10 we got. So this u3, so sorry, this x3 is equal to 10. That means in the second possibility, for the second possibility, we have u3 is equal to 10 by 3 we will get. So 10 by 3. So we will take this as our solution, our possible solution. So this is not feasible. This is already feasible, so we are not taking this. So we are going for this solution. So that means u3 equal to 10 by 3 we will get that solution. So then that means u3 we got. So in our problem, what the examiner has asked is you have to find out the u1, u2, u3 values, and that has to maximize, that will maximize u1 into u2 into u3 function, the function u1 into u2 into u3, subject to the u1 plus u2 plus u3 equal to 10 and u1 u2 u3 greater than or equal to 0. So u1 plus u2, from u1 plus u2 plus u3, that is we have taken as stage 3, and then u1 plus u2 we took as stage 2, then u1 we took stage 1. Okay, that means like our sub optimization, that means we have applied the sub optimization technique or concept in here also. Okay, that means like this. As we have considered u1, this is u1, and then stage 1, and this is u1 plus u2, then u1 plus u2 plus u3, last final. So and from this we got u3 is equal to 10 by 3. Then we can find, you have to move in the reverse direction so that you can find out u2 and u3, sorry, u2 and u1 also. So u3 is 10 by 3 and u3 u3 is 10 by 3, and we will get u2 is equal to, which is equal to x2 by 2. That means we got this relation from stage 2, and that will be equal to x2 is nothing but from equation 2, that is from stage 2 we have x3 minus u3 by 2. So x3 is, so we will get x3 is 10 and 1 by 2 taking outside, so 10 minus u3 10 by 3, so that will be equal to 10 by 3. Then you have to again go back to, from we moved from stage 3 to stage 2 and then again stage 1. So stage 1 we have u1 is equal to, from stage 1, x2 minus u2, and that will be equal to, from the stage 2 we have this 10 by 3, so you substitute for substitute for u2, and x2 also we have. X2 is x2 by 2 we have 10 by 3, so x2 will be 20 by 3, so 20 by 3 minus 10 by 3, that's it, 10 by 3. Then u1 you got. Now that means you got u1 equal to 10 by 3, that's equal to u2, that's equal to u3. So u1, u2, u3 all are 10 by 3. Now our problem is to maximize the how to find or maximize the function this is here, maximize u1 u2 u1 into u2 into u3. So you got u1 and u2 and u3 subject to this condition, that is design equation, and u1 u2 u3 greater than or equal to 0. So the maximum value will be 10 by 3 to 10 by 3 into 10 by 3 is equal to 1000 by 27. So this will be our answer. So this is the mathematical procedure of a dynamic programming problem, okay, by considering an example problem. So thank you.